Hello and welcome to section 6.3. So here we're going to start looking at exponential functions. So when working with exponential functions, we want to remember the laws of exponents. Alright, so these will basically are embedded throughout everything that we do with exponential functions. So if you have the same base and you're multiplying two factors, then the exponents add. If you divide, this basically will apply to division also, right? So if you divide things with the same base, then the exponents will subtract. That's minus t. Let's see if I can write that a little bit better. It's way to squeeze in there. The reason it's not written out right is because you can always kind of change the division to multiplication by multiplied by the reciprocal. So, but you can remember this rule also. If you have a base number raised to an exponent, then again to another exponent, the exponents multiply. If there's multiplication or division, okay, again this applies to division also, a over b to the s, then that exponent distributes to both of them. So we have as b over s if it's a division, as times b of s if it's multiplication. And the distribution rules do not apply if you're adding and subtracting, just if you're multiplying or dividing. 1 raised to any power is 1, a number raised to the 0 power is 1, and negative exponents mean reciprocals. So if you have anything to a negative exponent, then you write the reciprocal with that number to the positive exponent in the denominator. That's it, okay? So let's look at the definition. An exponential function is a function of this form, where we have a constant number times a base number to a variable power to the power x. So this is the parent function, the most basic exponential function we can think of. And of course we can adjust that by transformations, right? We can shift things left and right. We can, or up and down, by either adding values and subtracting from the exponent or from the whole function. We can reflect it by putting negatives in front or in front of the x. We can shrink it or stretch it by changing this number c. All right. This number c is important. So c is called the initial value. This is basically when x is 0. The function starts here. This is basically what the y-intercept is. A is called the base number, right? And this number tells you, it's like you start with the initial value c at x equals 0, and with each thing you increment, you multiply that by the base a. So when x is 1 is c times a, when x is 2 is c times a times a, when x is 3 is c times a times a times a. So at each stage, as you increase x, your value gets multiplied by the base number. That's called a growth factor, all right? So it's called the growth factor. So if a is bigger than 1, then the function actually grows. But if a is between 0 and 1, a fraction, then it's going to be negative growth, which is decay. Keep in mind that we only take positive values of a, so with exponential functions, we want to simplify them down so that that base is positive. Okay, if it's negative, we can factor out the negative and simplify it so we deal with positive bases. All right, so let's evaluate. So the exponential functions, you can evaluate them in a calculator. So we have a few examples here, base number evaluated to different exponents. Let me pull out a Desmos calculator. And then a scientific calculator. There we go. Scientific calculator. There it is. Okay, there we go. Okay, so let's look at 2 to the 2.7. So 2 to the power 2.7 and 6.498. Uh, 2 to the power 271. 2 to the, oops. Okay, I could just adjust that. 6.543. 2 to the 2718. Just adjust that. 6.5796, 6.580. Let's round to 2 decimal places. Alright, and 2 to the E. So E is this number. We'll talk about it in a little bit more. We're going to find this in our functions menu, 6.581. Right, so this number E that we just encountered is called the natural base. This often is the default base of an exponential function. It's very common in natural applications. That's why it's called the natural base. And you find it on the calculator. It has its own special button. So if you type E, it's 2.7128 and so on. This is an irrational number. It keeps going forever. And we'll work with it a little bit in this chapter. All right. Let's look at another example. Evaluate each exponential using a calculator. So we have 1 plus 0.09 divided by 12 to the power 24. This you can just plug in as is in the calculator. Use parentheses. So parentheses 1 plus 0.09 divided by 12 to the power 24. 1.196. A formula like this comes from looking at financial applications, like with compounding interest and interest rates and things like that. All right, let's look at this one. So evaluate this. Again, we just plug it in as we see in our calculator. So 83.6 times E to the power negative 0.157 negative 0.157 times 9.5. There you go, 18.813. Alright, so exponential functions are not difficult to calculate just using a regular calculator or a Desmos calculator. Alright, let's look at the next concept here. So now we want to look at some data tables and figure out whether the data in the tables is a linear function, an exponential, or neither. Right? If the functions are linear or exponential, we want to find the equations. Okay, so you figure out if it's linear or exponential by looking at how the values change. Okay, so for a linear, the slope or the change is constant. Slope is constant, which means, so for a linear, for constant changes in x, so for, this is change in x is constant, and then the change in y is constant. Right? So that basically means that as I increase x by the same amount, the y value will increase by the same amount. So as I increase x by a constant amount, I increase y by a constant amount. Alright, and the change in y over the change in x, this will be the slope. Okay, so for a linear function, the slope stays constant. Okay, now for an exponential function, as I increase x by the same amount, the y value would get multiplied by the same amount. The ratio of, not the difference as a linear, but the ratio of y values will need to stay constant. So as I increase x by a constant amount, y to the n plus 1 divided by y to the n will stay a constant amount. Right, so that means that if I look at any value and I divide by the previous one, y to the n plus 1 divided by n, that will stay constant always. Alright, so let's look at part A right here. So we can see that our x value changes constantly by 1, right? So I'm adding 1 each time. And now I have to figure out what happens to these values. Okay, so you can see that it's not linear because it's increasing by different amounts, right? 1/4 to 1 is an increase of 3/4. 1 to 4 is an increase of 3, 4 to 16 is an increase of 12, and so on. So it doesn't stay constant. Okay, so we know it's not linear. Alright, now let's check to see if it's exponential. Okay, so an exponential, we need the ratio of y value with its previous one to stay the same. Okay, so for example, if I compare these two, 1 divided by 1 over 4 is 4. Okay, if I look at these, 4 divided by 1 is 4. 16 divided by 4 is 4. And 64 divided by 4 is 4. Alright, so the ratio of the neighboring y will stay the same. Okay? Alright, so this is exponential. Alright, now we need to write our function. Okay, so the exponential function we know is c times a base number to the x. Alright? C is the initial amount. C is the value when x is 0. So we can see that we have that in our table already. When x is 0, the y value is 1. So C is 1. A, the base number, is the number that you're multiplying by each time to get to the next stage. So A is this ratio between neighboring y values. So A is 4. And then to the x power. Okay, so our function is f of x equals 1 times 4 to the x. So exponential equations are fairly straightforward to find from data, especially if you have the initial value. Alright, and you can verify, right? So if you plug in x is 0, you get 4 to the 0, which is 1. If you plug in x is 1, 4 to the 1 is 4. 4 to the 2 is 16, 4 to the 3 is 64, 4 to the negative 1 is 1 over 4. So you can see that that works out. Alright, let's look at part B. Alright, so our x values are increasing constantly. That's what happens to our y values. So if I check to see if it's linear, right? 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, 8 plus 2 is 10. So this is linear because you're adding the same amount, right? You can check some functions are both linear and exponential, but not this one, right? If you check the ratios here, right? If I do 4 divided by 2, I get 2. But 6 divided by 4 equals 1.5. So the ratios are not constant. So it's not exponential. So linear means that the equation is y equals mx plus b. Right? B is your y-intercept. So when x is 0, your y-intercept is 4. So mx plus 4. And m is the slope. M is, right, the ratio between the change in y over the change in x. So this is changing by 2 units plus 2 for every unit in x. So the slope is 2. So y equals 2x plus 4. And you can check by plugging in, right? When x is -1, we get 2. X is 0, we get 4. X is 1, we get 6. X is 2 is 8. Right, you can see it checks out. Alright, so that's how you check for exponential and logarithmic functions. Alright, now let's look at a bit of graphing. So we're going to graph some functions using transformations. Alright, so we want to be familiar with the graphs of our parent functions. Alright, so let's just do it on the same graph. We don't need to do it on the side. So if I want to plot 3 to the x, let's put some values in here in the table, and then we should start being familiar with what the shapes of the base parent exponential functions look like. But let's pick some positive values and some negative values and 0. So we have 3 to the 0, which is 1, 3 to the 1, which is 3, 3 to the 2 is 9, and 3 to the 3 is 27. Right? 3 to the -1 is 1/3, 3 to the -2 is 1/9, and 3 to the -3 is 1/27. Okay? So we can see that at 0, this is the y-intercept, is going to be at 1. 1 and 3, 2 and 9. On this side, -1 and 1/3, -2 and 1/9. Alright, and then so on. Okay? So what we'll notice on this side is that it gets bigger and bigger and goes up to -infinity. So that's the end behavior for x is positive. Right? For negative numbers, it gets closer and closer to 0. But it's never going to go negative, right? If you do 3 to the -100, that means 1/3 to 100. So that's never going to go negative. So on this side, it gets closer and closer to 0, so it hugs the x-axis, right? So exponential functions have a horizontal asymptote. So we have a horizontal asymptote over here. So for x is -infinity, the exponential 3 to the x is going to tend to 0. Okay, it doesn't go negative. So this is the parent function of that base of 3 to the x. Right? Now to graph 3 to the x minus 2, we look at transformation. We go, oh, this is a shift. This is going to go down 2 units. Okay. So that means the horizontal asymptote gets shifted down 2 units. So now it's going to be at y equals -2. Right? And all these values of y are going to be subtracted. Okay, so this one was y equals 3 to the x. If I draw y equals 3 to the x minus 2, we take these values and subtract 2. Okay, so this is 2 minus 1/27, whatever that is. 2 minus 1/9, 2 minus 1/3, And this is like negative 2 plus that. We're subtracting 2, so this is like negative 1 2/3. Negative 2 plus 1 is negative 1. Negative 2 plus 3 is 1. Negative 2 plus 9 equals 7. And negative 2 plus 27 equals 25. So all the y values get shifted 2 units down. Okay, so this one, 2 units down, 2 units down, 2 units down, and all these the same. Okay, so same shape, but the shift, vertical shift, like this. So this is 3x minus 2. Okay, all right, so that's the graph. Okay, so when you graph from now on, basically we want to keep this parent function in mind. Okay, so an exponential, so if we have a to the x, if the base a is bigger than 1, then this is going to be growth, right? Is going to have a y-intercept at 1 always. Okay, so again, this is a very basic one with the constant in front equals to 1. It's going to have a y-intercept of 1, and it's going to look like this. All right. If you increase a, so as you make this bigger, then the exponential function is going to get steeper. All right, so the bigger the a is, the steeper your exponential will be. And as you decrease a, it's going to become shallower. All right, so this is increasing a. Right? Now, if I have a is between 0 and 1, so a is between 0 and 1, so it's like a fraction, again a to the x, then this is going to be exponential decay. It's still going to have the y-intercept here, but it basically turns around. Right? So for any bases less than 1 or between 0 and 1, then it's decaying, it's decreasing. Okay, so as I change that fraction, then you're going to get different steepness. So if this is like 1/2, it's like this, but if it's 1/3, it decays faster. If it's 1/10, then it decays even faster. So as I increase that denominator, then the steepness increases too. Okay. All right, so these are like our bases, our parent function, and then anything that we graph, we can do by transformations. So we can shift things up and down, we can shift left and right, we can reflect either across the y or across the x-axis, and so on. All right, so let's look at the next one. So we have 3 to the x plus 2. Okay, so we notice our parent function is 3 to the x, so we can graph that first. And the plus 2, this is a movement of 2 units to the left. All right, so let's graph our parent function. As before, when x is 0, we get 1. When x is 1, we get 3. And when x is 2, we get 9. And on this side, 1/3, 1/9, and so on. Let's draw it like this. So this is 3 to the x. All right, and we know there is a horizontal asymptote at y equals 0. All right, so the transformation, the plus 2, is going to move it to the left. So there's no up and down shift, so the horizontal asymptote stays the same. But basically all my points are going to move 2 units to the left. So this one here at 2, 9 is going to move to 0, 9. At 1, 3 is going to move to negative 1, 3. At 0, 1 is going to move to negative 2, 1. This one moves 2 units. This one moves 2 units. Okay. So our function is going to look like this. Still with the same horizontal asymptote. So this is 3 to the x plus 2. Alright, that's it. So that's the procedure for drawing exponential functions. Remember what the parent function looks like and then shift it, stretch it, so on. Alright, let's look at this one. So let's see what's happening here. So we have our parent function. Then we have a negative in front. We gotta do that first. So this is a reflection across the x-axis. Reflect across x-axis. Alright, and then we have plus 1. This is going to be a vertical shift of 1 unit up. Alright, so we got to reflect first and then shift up. Okay, so let's draw our parent function. 1, 0, 1, 1, 3, 2, 9. 1, 10, 1, 9th. Okay, so we're going to draw our parent function here. And I'm going to put the horizontal asymptote at y equals 0. Alright, so this is 3 to the x. Our negative 3 to the x means we reflect. Okay, so all the y values turn negative. So 0, 1 goes to 0, negative 1. 1, 3 goes to 1, negative 3. And 2, 9 goes to 2, negative 9. And then the fraction ones are the same. Alright, we keep that same horizontal asymptote, but now the function is at the bottom. Oops. This is 3 to the negative 3 to the x. Alright, and now the plus 1 means that the reflected function is going to move up 1 unit. Okay, so all the y values, we add 1 to them. All right, so 0, negative 1 moves to 0, 0. 1, negative 3 moves to 1, negative 2. 2, negative 9 moves to 2, negative 8. The horizontal asymptote moves up 1 unit. Negative 1, 1/3 moves here, and so on. Okay, so it's the reflected function is going to shift up 1 unit. Right, so this is negative 3x plus 1. Let's do a better job there. Alright, there we go. So this is the function you want to graph. Now you can erase all the rest. You don't need like all the intermediary bits. I just wanted to show the process of doing it. So your final answer should be that reflected and shifted vertically one. Alright, let's look at D. Alright, so let's see what's happening here. We have 3 to the negative x. Alright, so it's the parent function is 3 to the x, but then this you have, this is a reflection across the y-axis. So this is reflect across the y-axis. And then the minus 1, this is a translation shift down by 1 unit. Okay. So we can draw our original function, our parent function, as usual. This is 3 to the x. Let's put the horizontal asymptote here. Then let's reflect across the y-axis. So that means it's going to flip over the y, so this stays the same. This goes to -1, 3, -2, 9, and same on the side. So this is 3 to the -x. Right. Notice that when you reflect across the y-axis, like growth becomes decay. And that should make sense because 3 to the -x means 1/3 to the x, which is 1/3 to the x. So when you have a negative exponent, it's basically like taking a base that's bigger than 1 and changing it to the reciprocal, the base that's less than 1. So it's going to turn into a decay. All right. And now the -1, we're going to move the asymptote down 1 unit. And then we're going to subtract the 1 from each of the y values. So let's do that on the graph. Right. And we get that function shifted down. Okay, so it's been reflected across the y-axis, 3 to -x, and then shifted down 1 unit. Okay, so that final graph is what you want. Okay, cool. So that's sort of some basics of graphing. Now, what we want to do with exponentials often to be able to solve application problems is to solve equations. Okay, so there's a couple of ways to solve an exponential equation. This section we're going to look at matching bases. So the rules say that if you have the same base with different exponents, then the exponents need to be equal. So we have a to an exponent here, let's call it m, and a to the n. Then the only way these could be equal is if m equals n. So if we get the same base, we basically can cancel it out and make an equation out of the exponents. Okay? So in part A, we have 5 to the x and 5 to the -6. Because the bases match, we say x equals -6. All right, so that's the solution. All right, let's look at B. 1/4x equals 1/64. So let's rewrite 1/64 means 1/4 to the 3. So we want to transform this side so it has the same base as that side. The bases match, and you go x has to equal to 3. All right. Let's look here. 4x squared 2 to the x. Change the 4. So 4 equals 2 squared to the x squared and 2 to the x. Exponent rule says that these exponents multiply. So this is 2 to the x squared, which equals to 2 to the x. Now my bases match, so I can get rid of them. We get 2x squared equals x. All right, so now we need to solve this. It's a quadratic equation, so we're going to subtract x, make it equal to 0. Factor an x, we get 2x minus 1. And we get two solutions. X is 0 or x equals 1/2. Right, so we have two possible solutions here. All right, let's look at D. So this has a base of 5. This has a base of 125. So we can rewrite 125 as 5 to the 3. 5x squared plus 8 equals 5 to the 3 to the 2x. 5x squared plus 8 equals 5 to the 6x. Bases match, we can get rid of them. X squared plus 8 equals 6x. Right, this is a quadratic, so we're going to put everything to one side. X squared minus 6x plus 8 equals 0. Factor x minus 4x minus 2. We get x equals 4 and x equals to 2. Yeah, that's it. Alright, let's look at these. Okay, so we have like 3 different bases, 9, 27, and 3. I noticed that they're all powers of 3. Okay, so 9 is 3 squared, and then that's to the 2x. 27 is 3 cubed, and that's to the x squared. And we have 3 to the negative 1. All right, now we got to simplify this. So in order to cancel bases, we have to have it in this form. Base to an exponent, same base to an exponent. Right now it's not like that because we still have some operations to do. So this is 3 to the 4x times 3 to the 3x squared equals 3 to the negative 1. Combine these into one base, so the exponents add. So 4x plus 3x squared equals 3 to the negative 1. Now we can get rid of the bases. When you have one base to an exponent equals another of the same base to an exponent, that's when they cancel out. So we have 3x squared plus 4x equals negative 1. 3x squared plus 4x plus 1 equals 0. English factors. 3x plus 1 and x plus 1. So x equals negative 1 over 3 and x equals negative 1. All right, those two solutions. All right, let's look at this one. Same deal, we got to simplify this. We have all the same base of e. So we have e to the 4x times e to the x squared equals e to the 12. Combine these into one base. We add the exponents. X squared plus 4x is e to the 12. Now we can get rid of the base. X squared plus 4x equals 12. Subtract x squared plus 4x minus 12 equals 0. Factor x plus 6, x minus 2 equal to 0. So we get x equals negative 6 and x equals to 2. Alright, so this is how the method of matching bases, and we can use these if we can rewrite each side of the equation with the same base. For a lot of exponentials, that's not possible, and we'll learn a new method that has to involve logarithmic functions, but we'll see that in the next couple of sections. Alright, let's look at these problems. In here, we want to write an exponential function whose graph is given. Alright, so we know, we're told that it's an exponential function. And we know that the basic exponential function is some constant. Alright, some constant times a to the x. And we could have a translation too. So we could have a translation here, up and down. If there's any horizontal shift, it would be absorbed in the c, so we don't need to worry about that. But we need to see if there's any vertical shift. Okay? And to figure that out, you've got to look at the horizontal asymptote. Alright, so here the horizontal asymptote is where it should be at y0. So that means there's no vertical shift. So this d equal to 0, and we don't need to worry about it. Okay? Alright, the c is going to be the y-intercept. Okay, so y-intercept is at 1. Alright, and the a is going to be how much we're multiplying by. Alright, so we can see that we can plug in a point, or we can just sort of deduce by looking at the points on the graph. I can see that here it's sort of going from 1 to 5, and here is from 1 over 5 to 1. So it looks like we're multiplying by 5 each time. Okay? Or we can plug in a point. Alright, so this is like the x and the y values. So when x is 1, y is 5. So we get 5 equals 1 times a to the 1. We get a equals 5. Okay? So our function is equal to 5 to the x. Alright. Okay, let's look at the next one. Okay, so we have this. We see that the horizontal asymptote hasn't moved up and down. So we're going to say that f of x equals c a to the x. Okay. We see that the y-intercept is -1, so this is going to be -1 times a to the x. We're going to pick a point on the graph and plug it in, so the y value is -e, and the x value is 1. And we solve for a, we get a equals e. So that's the base of the function. All right, so that means our equation is -1 times e to the x. There we go. All right, let's answer some questions about exponential functions. So suppose f of x is 3 to the x. What is f to the 4? So f to the 4 is plugging in x is 4, 3 to the 4 is 81. What point is on the graph of f? So because I plugged in x is 4, I got y equals 81. So we're basically graphing that point on the graph of 3 to the x. All right, part B. If f of x equals 1 over 9, what is x? So 1 over 9 equals 3 to the x. All right, we can see that this is 1 over 9 is 3 to the -2. So that means x equals -2. So the point on the graph is x is -2 and y is 1 over 9. Right, let's look at example 8. We have function 1/3 x minus 3. F to the -5 is equal to 1/3 to the -5 minus 3. So this is a negative exponent. We're going to do the reciprocal 1/3, which is 3 to the +5. This is 243 minus 3, so this is 240. So the point is x is -5 and y is 240. All right, f of x is 24. So 24 equals 1/3 x minus 3. We got to figure out what x is. Add 3 to both sides. 27 is 3 to the 3. 1/3 is 3 to the -1. So this is 3 to the -x. That means -x equals 3 or x equals -3. So the point that we found here was x equals -3 and y equals 24. All right, part C, find the 0 of f. So that means we need to solve 1/3 x minus 3 equal to 0. 1/3 to x equals 3. Change this to a base of 3. 3 to the -x equals 3 to the 1. So x equals -1. Alright, so this is when x equals -1, y is 0. So this is the x-intercept of the function, or the 0 of the function. Alright, that's it for this section.